I'm Marek, and I will give you a presentation directed at all sorts of interface designers. When we write programming languages, IDEs, like all kinds of software, those are really interfaces. This is the thin layer that stands between the user and the device. The goal of the user interface, if you didn't know, is to quickly and effortlessly translate actions of the user into the problem domain and translate the state of the problem domain into the thoughts in the user's head. And the interface is best when it's kind of invisible, when it's not there almost. And when we talk about using interfaces, there is one word which I really like. It's called automaticity. Scientifically, there is a different term for that. It's called procedural memory, or more commonly known as muscle memory. This is the ability to act, to navigate the user interface without giving it any conscious thought. We forget that we are using a mouse or a keyboard. We are just in there, in this other world. And we call this muscle memory, but it doesn't only affect motor memory. It also affects higher level parts of our kind of how we think. When chess players think about how they strategize in chess, they don't think about moving individual pieces. They recognize patterns, micro battles that they play simultaneously. There is also automaticity there. There is a procedural memory where they don't think about the detail, they think about higher level. So this is something that we want. This is our goal when we are designing user interface. We want to have the user transported into this other world. And one way of training user was created, a scientific method was created long ago by this guy. This is the father of modern gaming industry. He figured out how the same tricks that work in animals, they work perfectly fine with people. Those things are used everywhere. And this is actually a solid technique. This is based, people use this, and I think if the technique works, we shouldn't really worry about whether it's training involuntary responses or not. If it's useful, it should be applied. The problem with conditioning is not that it doesn't work, it's that the memory, the reflexes that it creates, this is not the type of procedural memory that we would like in our users. First of all, it seems that on a fundamental level, there are some differences in how this memory is even created in the brain. When we have a reward in this system, there needs to be a delay actually between a stimulus and the reward. Otherwise, the learning doesn't happen. So the neural mechanisms are different, but it also trains slightly. The memory, the reflexes that it trains are very surface level. They don't train the understanding of the problem domain. So how can we get automaticity? There is the hard way, through repetition. This is what we all do. When you force somebody to use a crappy interface over and over and over, after some time, they will become an expert. It just has to happen. We can use the reward system, but there is another way, and this is through immersion. So immersion relies on taking somebody who is already an expert in some domain and presenting a new problem as something that they already know. This is where user interface can help. This is why Scratch, the programming environment for kids, looks like pieces of puzzles, because this is what kids know how to do. When you present a new problem to them that looks like puzzles, they immediately get it. Slightly older kids, which played a lot of Minecraft, they may be more receptive to three-dimensional block-based programming, and this works. And the examples that I'm showing here, they are, I refer to kids because, this is easy. But whatever program you are designing, you are always designing for a group of people. So ask yourself this question: what are my users an expert with? And try in your interface imitate whatever they are an expert with. If they are a painter, try to make your interface resemble the tools that they use day to day. This will, or if they are a musician, they should resemble a musical instruments. Within reason, right? This is the point for the skeuomorphism. So in this presentation, I will give you some tricks about how you can So you may think that animation is hard because, quite frankly, it is hard, but there are some tricks to actually inject animation into arbitrary user interface. And in this presentation, I will give you exactly those tricks. So first, this intro that I just gave you, there is actually, animations are kind of controversial because there is this camp of people who think that immediate response is always like the better. And I largely agree with that. The reason we put animation in user interfaces is to make them more familiar to users. Like as the time goes on, we may kind of shorten the animations, make the interface more responsive. So now I will tell you about some animation techniques and give you some advice when we can use them. Then give you some like formulas. There will be a lot of code later on. So then we will look at the very common drag and drop problem, and then finally some just random assortment of tips. And there will be a lot of code, but at the end of the presentation there will be a QR code. So if you want, you can just scan this and see this in your device. Many of the animations, they look much nicer on high refresh rate displays. So yeah, I recommend that. Okay, where the animation even comes from? It actually comes from the music industry, sorry, not music, movie industry. They were first there. All of the techniques that like we started with when animating computer interfaces, they are based either on those like mathematically based nodes that we can use to animate values, like in Blender, for instance. We can capture the motion of like real actors using motion capture, or we can do stop motion animation. And even though this may seem like this is like stuff from movie industry, you may need special software. Actually, CSS has amazing support for this type of animation. All of those, actually. There is this like keyframes block that you can inject in your web page. And if you can capture some motion of a user using a webcam or something, like translating this into a keyframes block, it's just a mechanical transformation. You just have to change the format from CSV to a sequence of values for keyframes. The issue with timeline-based animation is obviously the interactivity. So in my presentation, when I quickly switch slides, you can see that when I press the button, the animation stops. There is this lag. The browser doesn't know how to like maintain the speed. It just restarts the animation from scratch. This is the only kind of issue with timeline animation. If we don't control the animation by using a fixed timeline, we control it by code. One specific type of code-driven animation is one based on physics simulations. This is the most powerful approach if you're writing a game, and this is what you go for. There are 3 issues with simulation-driven animation, each of which is solvable, but each of them is it's a talk in itself. First of all, we have the problem of springy attachment. You may think it's solvable, but then you encounter the physics constraints that... So if you move any object on screen by affecting its position, you may break like key constraints of the physics solver that will cause objects to go through walls and do all sorts of funny stuff that you may be familiar with, like from games. Then there is a smaller issue with synchronization with the display refresh rate. Because physics engine usually runs at some fixed tick rate, we can vary it a little bit, but that makes the simulation less deterministic. So this is another smaller issue, also solvable. And lastly, there is a problem of power draw. Our devices actually don't like to be woken up, even if we don't use them a lot. Like physics simulation is super cheap, but the CPU doesn't like to be woken up like 60 times per second to do like nothing, essentially. When we look at those 2 types of animation, there is one very simple heuristic when to use them. So if your goal is to tell a story, this is when you go for timeline-based animation. If you want to present the state of the system, this is when you want to go for the procedural one. And I would like to talk a little bit about a specific type of procedural animation where we simplify things as much as we can. So instead of simulating the whole system, like a gravity between a planet and a cursor, we can derive the parameters of the orbit. When we do this once, we have like an analytic function that tells us where the planet is at any point in time. We could like tell where it will be in 10 years. This is easier to integrate with our code because at every display refresh rate, we just call a function which gives us the position of the object, but it's also a little bit limited because we cannot really simulate the stuff that we used to simulate with physics engines. This is widely used, but it doesn't have a name. I think it should have a name. I'm just bad with naming. I just call this analytic animation, but it's a very old idea. Many games use this kind of animation to actually drive stuff on screen. The function that we will use throughout this presentation is based on this kind of idea. Let's say we have three variables: our value, a target value, and a delta t that we want to kind of, as time progresses, we want our value to get closer to the target. So regardless of the starting point that we start from, we want to approach the target. This is a simple formulation, and we can look at the first type of approach function that we could have. So this is a function that takes those three variables that I showed you: value, velocity, target, delta t. Velocity is actually a parameter that we can control that tells us how quickly or how slowly we will approach the target. This type of animation it looks a little bit wonky. It was like very popular in like retro games, but it is still the best type of animation if you want to animate color transitions, transparency, all sorts of lighting effects. Some games, such as like Factorio, it actually uses the linear approach because of its simplicity. It's very easy to simulate movement of huge number of objects because their movement is very predictable. Okay, so that was one. But this is not the most popular approach used by games. The most popular approach is actually this one. And it is popular because this is the whole formula. So lerp function, if you're not familiar with that, is the linear interpolation. It takes two values and it returns a value between those two values at a fixed ratio between them. This gives us this kind of movement, which is very fast at the start, very slow at the end. And if you're familiar with Wilhelm scream, if you look at this animation for long enough, you will start to see it everywhere. Like every game uses that. Like changing the sizes of buttons, like moving stuff on screen. It's really, you cannot, from this point, you will not be able to play any game without noticing exponential approach. This function can be, this is a discrete variant. We have to apply this after every like animation tick, animation frame. We can convert it to a continuous version using the, well, exponent function. And this allows us to also control like the shape, how quickly we approach the target in a slightly more easy to parameterize way. So this is one way to write this function. But there is like a different, like a representation on this, which I use to kind of flex my knowledge of this exp_m1 version. It's not more performant. It's totally equivalent. It's just, yeah. Okay. So the next thing we want to animate is usually periodic values. Sometimes when we have a value which should rotate, the best way to approach a value which is very high from a value which is very low is to actually go down and wrap around and approach it from the top. So the key thing that we need to do to like implement this kind of behavior is to, so if you have a value, one thing that you can do with this value is you can add a period or subtract a period. And visually, for the user, nothing is going to change. But numerically, you can move your value closer or further away from the target. So there is this thing that you can inject. So before you animate stuff, you just insert those two loops. And if the value is too far from the target, you just shift it by a period so that it's closer, either down or up. And as a result, yeah, you will always approach the target from the closest kind of arc that you can. This version, this solution, actually has while loops, and while loops may seem scary. They don't execute like that much. Actually, most of the time, they will not execute even once. But you may be tempted to write a solution based on modulo. And I invite you to try. I tried and failed. JavaScript has a very funky semantics for the modulo operation, especially around negative values. Luckily, okay, maybe not luckily, but if you're in C++, C++ has like 5 different modulo, like remainder functions, and this one just happens to be like the perfect one. So instead of those 2 loops, you can also use something like that. I just haven't been able to translate this to JavaScript. Okay, so we actually covered the basics. So with linear approach, exponential approach, and this rotational trick, you can probably animate, like, you're ready to like start game development. But we can actually make these things more complicated and more interesting if we introduce some velocity. We will represent the velocity as an arrow. This constrains our solution so that the path that we take has to be tangent to the velocity vector. No. And yeah, we essentially have to match some function to touch this point and be tangent to velocity. One function that I started with was the sine approach. This is just a sine wave, which is just rescaled so that it fits within half a period around 0 and has amplitude equal to amplitude. In this equation, this is fixed, period. This is something that we parameterize our animation with, but we have 2 variables. We have amplitude and t. This thing is actually slightly harder to solve than the other ones, and the code is also going to be slightly longer. This is how it looks like. But so what we are doing here is first we are finding the amplitude, then we are putting some constraints because we don't want to like find bad solutions which are totally out of our domain, and then we are finding the horizontal argument, and finally animating the value. This function returns 2 values. This is our new value, our new velocity, and this type of motion has a smooth acceleration. Like this is its main advantage. Because it has this slow acceleration, we can use it to simulate heaviness if we like use a very long period. And this is relevant in user interfaces because if you think where your user is looking in the interface and you want to draw the attention of the user to some space, you know, on the periphery of their vision, this is a very good kind of approach because it spends a lot of time accelerating so the user has time to actually see where the value is coming from. Let's complicate things even more. Here we have 2 parameters. So there is first a period, and there is so we are combining the sine wave that we had before with exponential function. The 2 parameters described how wavy the function is and how quickly we are approaching the target. Again, we have 2 variables that we need to solve with. The solution to this one is even messier. I haven't been able to find a great one, but I found something that works. And again, this is a code that you can just copy, paste it into your project. This is like all public domain. Feel free to use that. Or feel free to translate it to your favorite language. This one has more parameters. We can specify the initial velocity. Usually the initial velocity will be around 0. We can specify how quickly we want to approach the 0. And if we parameterize it, it's almost like the previous one, like the sine approach, but with the added benefit of like introducing wiggliness. So if we decrease this wiggliness period, we get a super wavy behavior. Okay. This is a good time to compare this thing to a physics simulation. Physics simulation or a timeline animation, we usually don't think of code bloat when we write in JavaScript because it's just so commonplace. But bringing in a simulation engine or like a timeline, but animating with timeline also requires like an animation engine. There is a different amount of code that we need to bring. If we can try to animate a value with a single function, this will always result in less code bloat than a full animation library. It's also slightly easier to parameterize. If we try to parameterize like movement of a button using like a physics engine, we have to come up with a mass, like how many kilograms is this button, or how strong is the spring which holds it into place, how many newtons per meter it kind of has. And I have even no idea what's the unit for damping. The state is also easier to manage. In this approach, we have just value, velocity, as opposed to the whole physics engine. Accuracy is pretty decent. The accuracy of timeline approach is also excellent. I haven't included timeline in this comparison, but it's very good. The simulation, like I said, I mentioned that it requires some work. Okay. So let's look at objects in motion. So I came here by train. If you're traveling at a high speed and you look out of the window, you can see objects passing you by. Most of the time they will be blurry. But if you focus your vision on an object, then for a brief moment you can actually get to see it sharp. You can actually read even text, from objects which are moving very fast but closely. This is like the thing that our eyes have, where we can just notice stuff. This is not the case for computer screens, because computers display animation as a series of still images. When you have anything that moves on a computer screen, your eyes behave as if they are following a moving object, but the object actually jumps. So even though the object is sharp on screen, you see it as a series of blurry ghosts. I even have this small example here. I can wave this thing, and you should be able to see the dude here, very sharp. But if you try to focus your eyesight on this guy, like on the background, you will see that if you really focus your eyes, the background gets a little bit blurry, but the guy stays sharp. Your eyes are following him. Your eyelids are getting heavy. So there is this middle motion of the movement. This is actually the problem. Not the problem. This is the blurry phase of the motion. The acceleration phase is actually fairly sharp. The deceleration is also fairly sharp. But we could design an animation curve which totally avoids this blurry phase. And I said before that we should simulate realistic environments. Let's forget about this. This is not going to be realistic. Let's try to come up with a function that looks like that. This is more of a geometric kind of approach. We will try to follow a circle, then jump to another circle, and approach our target. This is, I call this warp approach, because it's this is how it works. The solution is very comparable to the others. It's not longer, not shorter. And yeah. This is roughly how it looks. I like setting warp time at 1. If we set the warp distance so that it's long enough, we are getting this nice wavy approach. But if we want the object to jump, we can specify that, for example, after 30 pixels, roughly, it should jump to the target. This is a new thing. I haven't been able to use this in any project yet, but it looks cool, and I'm just looking for opportunities. So now we can take a look at all of those approaches and try to compare them. You can here, if you look at this red ball, you can see this blurriness. If you really try to follow the ball, you will see a couple of ghosts following each other. So what I like about the warp approach is that it seems like, just look at this section of the screen. When they leave in this direction, the spaceship is the last one to depart. So it stays very long in the starting position. But it's also one of the first one to arrive at the destination. Yeah. So those are the animation tricks, functions that I wanted to show to you. And now let's look at the dragging issue, the dragging animation. So this is the typical way to implement dragging, and it's a good one. So basically, on each animation frame, we are moving our object towards the mouse position. So target X is mouse X, target Y is mouse Y. This is what we are interested in. Don't care about those. But there is this springy behavior, right? When I hold my mouse and when I move it, the planet just oscillates, jumps around. I don't want that. I want the planet to be connected to my hand. The way to solve this, usually, is to just offset the screen position of the object by the mouse delta. But there is a problem with that, because it will mess up like everything else, so we have to be careful. Let's not do that yet. So let's still have a springy animation. This is the same animation as before. I move my mouse, the planet follows. Let's try to snap it to those corner positions. We will do this with a function that takes a position on screen and returns a new position. When I move my mouse here, the function is an identity. It returns the same position as the mouse. But when I'm too close to the corner, it returns the snapping position. So now I have a planet that snaps. And this is the point where I can actually implement this responsive snapping. And the trick is, I'm looking at the snap position across the frames. And only when the snap position between frames is different, then I apply the mouse delta. Maybe messy. This is something that you have to kind of look at this slide for a couple of minutes, probably offline, to figure out what's happening. The effect is that the planet still jumps. It animates into correct positions. Or not so correct, but this is the CSS fault. But it stays connected to my mouse. I can move my mouse. It's like really sticky, really responsive. Okay, but that was a very simple case because I have this. It's like cheating. I have this object in a global coordinate system. I can move it everywhere on screen. Super simple. If you are writing any realistic applications, you have like a tree of widgets. And you have a widget which is like in one position in this tree, and you move it to another position in the tree. So the way to animate its movement is as follows. So first we find its initial position. There is a picture. Let's call this A. So this is the starting position. Then we reparent the object immediately, so it snaps into place into the new position. Then we find the new transform B. And then we follow this path. We follow the B in reverse, and then A, and we shift the object to this original position, and then decay the animation. And this is how it looks in real time, and it may seem like the star is actually on a separate layer, but it's actually not, and there is I have a code to prove it. It's actually being reparented as I'm moving the mouse, but because I'm applying this offset trick, it feels like the mouse has a smooth, it moves smoothly between objects, between containers. And this slide actually has an error because this should not be here. The proper way to express this is important, is to actually follow minus B first and then A. There is no such thing as A minus B. This is important because of matrices. Matrices care about order of operations. So we can display objects on screen with matrices. So matrices, for anyone who doesn't know, whenever we have an object on screen, we can express its transformation as something like that. This is a matrix for two-dimensional objects. Elements of this matrix are easy to interpret. This is the scaling in X, scaling in Y, translate in X, translate in Y. It's easy to construct. When we have a local coordinate of an object, we multiply it by a matrix like that to get a screen coordinate. And if we use the same trick as before, but with matrices, we can do smooth animations not only for the position of objects, but also for rotations of objects and scaling of objects. So this is an example where an object is being grabbed from one coordinate system, and it smoothly transitions to another. And this is the same trick as this slide. We just have to take those transforms not as positions, not as client rect, but as matrices. Bad news is that JavaScript has a mixed support for matrices. It's there, so you can apply a transform style to any CSS element, and you can get that in JavaScript, but I haven't seen anyone being able to recover the full transform matrix. This CTM is what is important here. There are some documentations on Mozilla Developer Network about this. So if you're interested in that, you can probably make it work. It seems doable. It's just nobody has done it so far. If you're working with Canvas, because JavaScript also has Canvas, Canvas has a great support for matrices. So if you're using Canvas, you're at home. Okay. Next thing, like I mentioned, power draw. This is very easy to avoid. Basically, when there is nothing to animate, we want to stop the animation. It's easy to just call a request animation frame, which will constantly render the animation. We just don't call it anymore. If we don't have anything to draw, don't call request animation frame. You can use this variable needs animation frame. If you structure your loop like that, it's super easy to avoid power draw. Even this slideshow uses this trick to reduce power draw. Very simple. Then, okay, this is controversial because I see all over the place people fighting with tearing, treating it as it's something bad. And I kind of disagree. I think tearing is a problem only in some domains. If you have a large object, vertically large object that moves quickly across the screen, this is when it's a problem. All other situations and user interfaces almost never have large objects moving horizontally. And people who game, they recognize this issue, and everybody who's competitive gamer plays with vsync disabled because we want that extra tearing. This means that the latency of a new frame arriving on screen is lower by on average half a frame. Actually, it's larger. In this case, you can see that the tear is here. So everything that's here is 16 milliseconds faster. And this is the baseline. This is what we would see if we had vsync enabled. And this is so 80% of the screen is actually rendered faster. In user interfaces, you will not see this, only in side-scrolling games or FPS games. In FPS games, it's actually very visible. The difficulty with tearing is that it's not super actionable unless you can develop natively. But if you're using something like Electron to deploy your application, there are switches that you can pass to Electron to actually force it to disable vertical synchronization and bring the latency a little bit down. Okay, and one more tip about end-to-end latency. So if you think about the path from the CPU, from your code, to the human brain, there is actually some research about how quickly human brain processes information following different paths. And if you go through years, I don't know why, but apparently it's faster. You get 2 frames of latency if you just signal information through sound. Sound has this funny issue that it travels slowly through air, actually very slowly. So at this kind of latencies, it's actually relevant whether the user has headphones or has a phone in their hand or is looking at a television, which is a couple of meters away from them. And that distance is actually going to be a factor. Usually, though, the perception latency is the dominating factor here. One key thing here, I'm ignoring hardware latencies here. This is just the latency. This 10 milliseconds and this 16 milliseconds is just the latency coming from synchronization and size of buffers. 10 milliseconds is very tight. To actually get 10 milliseconds, you have to use the right operating system APIs. Browsers do this natively, so you don't have to worry about anything. But if you're implementing something on yourself, you have to care about that. And if you're implementing something yourself, you can actually bring this even lower to around 2 milliseconds. And yeah, this is it. Thank you.
Hey, thanks. That was really great. Thank you. I wanted to ask, like, there's so many different things to choose from when like picking an animation function, right? Like how do you go about, sitting down and thinking, right, what are my options? What's the best one to do? Like, do you have like a cheat sheet or something, or do you just like have it all up here? Do you like play around? I'm just wondering about that process, because that's something I struggle with.
Yeah. So the first thing I think is, do I want to really bring the latency down, or do I want to get some artistic effect? Because this is like the most important thing usually. Sometimes you want to signal something through the animation, like heaviness or lightness. This is why the feather, like here, was presented as a feather. The exponential approach is like, it simulates very light objects that are like landing on the target. And the sine wave, it's more like accelerating and stopping slowly. And the length of the animation is also something that's fun to play with, especially if you take it to extreme. So don't use, like the middle length of animation is never interesting. It's always funnier if you like just crank it like to 2 frames, like make the animation like 50 milliseconds long, or make it 5 seconds long. Those extremes usually give like nicer effects. Yeah, thanks for the question.
Thank you very much for more ideas for animation. I thought about this a lot, but you had more things to think about. One thing I'm curious about, because I haven't done the sine approach, and you mentioned it having velocity, but is it like interruptible in the way that a physicsy or springy simulation is? Like if the target changes in the middle of the animation, what happens in the sine approach?
This is actually the whole point. So we have to recompute those trajectories every frame. So every frame the target can move, every frame the target can change. I have a demo. It's crashing, so I'm reluctant. But when I move stuff, so this is the snapping. Like I showed you the HTML animation of snapping. So when I pick the object from a toolbar here, it actually goes from like one widget, one branch of the widget tree into another branch, and like there is a smooth animation there. The eyes of this kind of parrot, they are animated to some degree. Other elements of the system are also animated. Like the clock has a wiggly kind of spring. Yeah, it's so cheap to insert animations. When animation is just a single function, it doesn't carry any state. It doesn't cost you really anything to just inject it everywhere. It may be a little bit annoying, so be reasonable, but yeah.
On the question of little annoying things, so how, in case of this oscillating and slowly decaying animations, how do you choose decay stop point that animation still looks realistic enough but not oscillate until...
Okay, I know what you're talking about, because this is a very common problem. So the thing with oscillating animation is that it will forever just approach the target until we reach the float accuracy, like the epsilon of float accuracy. So the thing is, you take a look at the position before and position after. If they are the same, this is when you stop the animation. This means the animation is fairly long, so even after the object apparently stops moving, like it sits there in place, but the animation still kind of animates like really tiny, totally imperceptible, offsets. Eventually it will stop. It just takes a couple more seconds to stop the animation this way. It's a very robust trick to stop the animation. You just compare the value before the animation, after the animation. If it's the same, means it's over. Yeah, this plays into this power saving thing, because when the animation stops, you really want to like send the PC, like the CPU, to sleep.
Other questions?
Hey, thank you. That was great. I'm kind of curious because you showed us something that you are building that looked very intricate and very neat, and I'm very curious, what are your inspirations? I feel like this must come from somewhere, that you want to craft something that has such kind of detail in its interaction And yeah, I would be curious to hear where you got inspired.
This is only a matter of spending enough time with your computer and having just time to play with things. You know, just
Self-inspiration.
yeah, that's the inspiration. Yeah.
I have a question. So, amazing toolbox and set of techniques. I think a couple times you're like, oh yeah, this is simple. Leave it as an exercise to the user. That was fun too. And where do we go to start thinking about, I think of trends in design, I think of flat design, I think skeuomorphism, and I think about, we use words like malleable software, which to me suggests interactivity and motion more. Mm-hmm. So where does one go, perhaps as someone who's less informed about design, to even just start, getting inspired? Mm-hmm. Kind of the same questions, not on yourself, but like, are there toolkits? Are there other things that you can recommend to kind of do a little shopping for effects I might want to add?
Actually, if you're like new and starting, you are in an awesome position because you haven't been kind of poisoned by the dominant ideas which are everywhere. If you're trying to implement like a cool interface, think from your own perspective what would work nicely, how your ideal workflow would look like. Because sometimes there are some ideas that we implicitly take from others and we don't even we forget that we even took them. Reinventing interface from scratch is nice, and I think you're only in this position to do this if you're like starting fresh and you don't have experience. So if you can, try to not look at Twitter and try to not to look at what other people are building, but just play with code, see what happens. Like put a slider to the extreme and see how it behaves.
Okay, so basically, I'm just going to ask every speaker, so people can just make things. That's lovely. Thank you very much, Marek.